we said that related rates problems are big implicit differentiation problems that we do to find out how the way some variable changes is related to how some other variable changes at the same time. So here I have an example. It's the bottom of that front page of your 4.6 handout. The volume of a cone with radius r and height h, we know. Interesting, I called it v of t. You might have just called it v. If the radius and the height are both changing, what's going to happen to the cone? If the radius and the height are both increasing, what's going to happen to the cone? It must be growing, right? So I happen to know that they are both increasing at a constant rate of 0.5 centimeter per second. Then what is the rate in cubic centimeters per second at which the volume is changing? And I'm expecting that answer is going to be positive because I just said my volume is increasing, so the rate of change of the volume with respect to time must be positive. Okay, and what is the rate of change of the volume when, at the exact moment when the height is 9 and the radius is 6 centimeters? So, what do I know? So the first thing we want to do is figure out what rates we already know and what rate we're looking for. So I've been asked to find the rate the volume is changing. So it's going to be called dv dt. Some things we already know. We know the radius is changing at a constant rate of 1/2. That's going to be dr dt. We know the height is changing at a constant rate of 1/2 centimeter per second. So we know dr dt. We know dh dt. We know we want to freeze the picture at one specific moment in time when height is 9 centimeters and radius is 6. And the thing we're looking for is dv dt. How fast is the volume changing with respect to time? Okay, so we seek dv dt at the moment described. We know dr dt and we know dh dt. So the thing I need, here you might find a picture helpful, but I think we already know, it's a little, they've sort of handed to us a formula. We need some equation that relates not the derivatives that we have and that we're looking for, but the original variables whose derivatives we happen to have. So we need something that relates v and r and h. I think it's pretty clear here. We've been given this formula. So you can jump right to this next step, which is we know we're going to start with this equation, v equals 1/3 pi r squared h. My next step, I'm going to take the derivative of both sides of this equation with respect to time. Oh, here's the first problem. I'm hoping you're okay up through those steps. We needed an equation that related volume, height, and radius. Kind of one that was already sort of prepackaged for us. But when it's time to take the derivative of that equation, of both sides of that equation with respect to time, I have this extra wrinkle, which is volume is a function of two separate variables, radius and height. So when it's time to take the derivative of volume with respect to time, I'm going to have to use the product rule. So I'm going to think of volume as 1/3 times pi r squared times h. So those are my u and my v. So I'm going to think about the product rule, which is going to be derivative of the first times the second, plus the second times the derivative of the first times the second, plus the second, why can't I say that right? The derivative of the first times the second, plus the first times the derivative of the second, is one way to say it. So, notice here, in my mind, first is 1/3 pi r squared, and that contains the variable r, so I'm going to pretend I'm taking the derivative with respect to r, and I'm going to have to multiply by the derivative of r with respect to t, because t is the variable I really wanted to be taking the derivative with respect to. But just notice that all along here, I have the r that I'm pretending to take the derivative with respect to, I have the t that I'm really taking the derivative with respect to, and I have this h that's another multiplier. So I have all these factors in play as I take this first derivative. So this is 1/3 pi r squared. The 2 from the r squared comes to the front to multiply. I have the 1/3 times pi times r has a new exponent, which is 1 less. Now I acknowledge that I was really taking the derivative with respect to time, so I multiply by dr dt. That's the derivative of the first. Don't forget I need a times the second, and my second was h, so that's where this h comes from. Plus the first, just the way it was, 1/3 pi r squared, times the derivative of the second. So 1/3 pi r squared times the derivative of h with respect to t is dh dt. So once I have this, once I've taken the derivative of both sides with respect to time, my next step is, now it would be okay. Now that I've taken a derivative, it's okay to freeze this equation in time. It's okay to substitute in values that I've been told, even if they're values that only apply at a certain moment in time. So I already know dr dt and dh dt each equal 1/2. I've been asked to freeze the problem at the moment when r is 6 and h is 9. So that's my next step, is I'm going to replace these values. Things that I replaced, I wrote in red, just to sort of make it clear what happened here. So the 2 times the 1/3 pi r to the first, I can now write as 6 to the first. Dr dt is 1/2 times h. H, I've been told, is 9. Plus 1/3 pi times r squared. Instead of r, I can use the 6 times dh dt. dh dt is 1/2. Again, I could have included units in all my work here. I think it's probably, well, and please feel free to. It's probably just as obvious at the end. In fact, I don't even need to worry about the units. I've already been told in this problem that the units on my answer are going to be cubic centimeters per second. Okay, so this expression, if you're taking the multiple choice part, you're going to have to simplify it. This was a multiple choice question. If you're taking the free response section, feel free to leave your answer like that. You have no obligation to simplify. But again, this is a multiple choice question, so I've simplified each of those expressions. I come to the place where dv dt equals 18 pi plus 6 pi. I don't think anybody would fault you for that answer. If you want to be super specific, I'm computing dv dt, the rate of change of the volume with respect to time, at a particular moment in time, the exact moment when h equals 9 and r equals 6. This is the notation you can use to say that. But in either case, this is a multiple choice question. We're looking for one final numerical answer, and that is 24 pi. I just want to take a second to compare these last 3 examples to the example that we did in the video before, which is, I think, there was the volume of a sphere, and it was how fast is the volume changing at a certain time. That's sort of a pretty straightforward kind of way that they might test related rates on the AP test. You didn't have to go very far to figure out the equation to relate all your variables. There was only one variable in the equation. Taking the derivative was probably not a big deal. I'm hoping it wasn't a big deal. And it was sort of straightforward to substitute in those numbers. I don't think that there was any confusion about the units. So that's good. There might very well be a related rates problem that has no complications in it on the AP test. There's probably very likely going to be a second problem on the AP test that's a related rates problem that has a little more something to it. So it's very unlikely that it would be complicated on 3 levels. But these last 3 problems are examples of related rates problems that are each complicated in their own kind of way. The last example we did of the volume of the cone, that was complicated taking the derivative of the equation we had. It was easy to find the equation, they gave it to us. But taking the derivative was complicated because that had 2 variables in it, so we had to make sure we stopped and used the product rule. So here is a second example. I don't think that you will find taking the derivative of this equation difficult, but you're going to have to make a picture to come up with the right equation and to make sure that you have the right rates of change that you know. So check out how this is different, complicated in a different kind of way, but still a related rates problem. So this is pretty common. Cars approaching an intersection is a good related rates problem. So the police car, it's coming in at an intersection from the north. It's chasing some bad guys who already went through that intersection and turned east. And they know that at the exact moment when the police are 0.6 miles north of the intersection and the bad guys are 0.8 miles east, they can radar gun the bad guys and figure out how far apart, like how fast that distance between them is changing. can you use that information to figure out how fast the speeders are speeding? So, yes, you can. This is a really excellent example of a related rates problem where you probably want to have a picture in place. You might even like to have a picture in place before you try to figure out what you know and what you don't know yet. But some things that we do know, we won't use variables yet, but we'll say that. Same moment. Well, what is the thing that we're looking for? The speed of the car. Remember, the speeders are going east. That's north. So this is east. So the speeders are going this direction, and the thing we're looking for is their rate of change, the rate of change of their distance. So we don't have variables in place yet, but if we decide that we want to call that x, then we're going to be looking for dx dt. So I'm going to make a picture next. Alright, so here's my picture again. This is, whoops, this is north up here. The first thing I put in this picture, I put in this little 4 arrow thing because I thought that kind of looked like an intersection. So I know the police are coming from the north toward the intersection. So I'm going to put P for police up here, and they're coming toward the intersection. So you might like to put an arrow along that picture here to show that the police are above the intersection and they're getting closer. The speeders were at the intersection, but now they're driving this way, getting further away from the intersection. So some things that we know. I'm going to make 2 versions of this picture. I'm going to make the version that is always true. And then I'm going to make a second version where I freeze at a specific moment in time. For some people, if you try to put both sets of information on one picture, it can be very confusing. You can end up trying to accidentally plug some numbers in before you take your derivative, which is going to give you the wrong answer. So, things I know. Do I know how fast the police are going? So, the police are going 60 miles an hour. So here's what we want to do. I'm going to call that distance x, the distance between the speeders and the intersection. I called it x because it's sort of a horizontal distance. I'm going to call this y because in the way I've oriented this picture, it looks like a vertical distance. And the actual distance between the police car, which is here, and the speeders who are here, is whatever this hypotenuse of the right triangle is. Pretty common scenario for a related rates problem. So what do I know? Okay, I know that the police are going 60 miles an hour. So I'm going to call this y. I have to ask myself, is the vertical leg of that triangle getting longer or shorter? Well, it's getting shorter because the police are driving toward the intersection. So I have to use that information along with this information that they're going 60 miles an hour to say that dy dt is negative 60. That's the trickiest part in this whole problem, is to realize that the rate of change of y, since y is getting shorter, must be negative. So the thing I want, I called this x. I know the speeders are going this way. And their rate of change, the rate of change of their distance, that's the thing I'm looking for. I don't know what it is, but I'm going to call it dx dt. That's the rate of change of the distance of the car from the intersection. And I do know, if you want to call this z, just for that, there's some moment in time where this is true. dy dt is negative 60, dx dt, we don't know, we want to find it. And dz dt, they're saying, is the distance between the two vehicles increasing? It is, it's increasing, which means dz dt must be 20, positive 20. So dz dt equals 20. I'm sorry, that's not easier to read. But dz dt equals 20. So thought maybe it'd be good to go back and do that in different colors. So I wrote names of variables in blue. dx dt is how fast the distance between the intersection and the speeders is changing. That's the thing I want. I'm going to put equals question mark. dz dt is how fast the distance between the police and the speeders is changing. We've been told that is 20. Specifically been told that distance is increasing, so we know that rate of change is positive 20. And dy dt, we know that the police are approaching the intersection at 60 miles an hour, which means y is getting shorter, so I'm going to make a note that dy dt equals negative 60. So I can make this decision. The thing I'm looking for, it's called, in my picture, now that I've labeled my picture with variables, the thing I'm looking for is dx dt. I know a little something about dy dt and dz dt. So if I can figure this much out, then I know the way I'm going to start in this problem is I'm going to have to write an equation that relates x and y and z. And I'm hoping you've already thought about this. The way to connect those three variables, they're related by the Pythagorean theorem, right? So I know that x squared plus y squared is going to equal z squared. You can see I wrote my equation in there. It's got a little dz dt on top of it. But now I have my equation. Now it's okay to try to freeze my picture. There's two things I have to do, right? Now it's okay to freeze my picture, and the reason I want to freeze my picture is because I'm going to need some number values that I can substitute into the derivative of this equation. So I'm going to take that derivative next, my derivative with respect to time of the equation x squared plus y squared equals z squared. So to take the derivative of x squared with respect to time, I pretend I'm taking the derivative of x squared with respect to x, which is 2x, and then multiply by dx dt. So here's my derivative. I'll get this guy out of the way. So 2x dx dt plus 2y dy dt equals 2z dz dt. If at this moment you notice that you could divide every term in that equation by 2, totally up to you. Now we just let the algebra take over. I'm trying to isolate dx dt, which means I'm going to want to be able to substitute in some sort of value for every other variable in here. So that's what I'm going to try to do. And then that thing that I need in order to make this happen, I'm going to need some of these values that I've been told about. There's a moment when the police car is 0.6 miles north of the intersection. That tells me that there's a moment when y equals 0.6. At that moment, x equals, I'm going to put these in red just so I can see that they're different from the purples and the blues. X is 0.8. So, does that help me? It's going to be time to replace. I'm going to want dx dt, which means I'm going to need to plug something in for x, for y, for dy dt. I have all of these so far. I'm going to need to substitute something in for dz dt, which I know. It was purple. I just erased it. I'm also going to need to substitute in something for z. So this problem does have one missing piece of information that I have to stop and use geometry to figure out. At the exact moment when this is 0.6 and this is 0.8, could you figure out what the hypotenuse of that right triangle is? So that's a 6, 8, 10 right triangle is one way to think about it. You can use the Pythagorean 0.6 squared plus 0.8 squared equals question mark squared, and we can figure out that at that exact moment in time when y is 0.6 and x is 0.8, z is equal to 1. Now I can make substitutions in for all of these values. So you can see here I've made substitutions in for all the values I didn't know. It's my job now to isolate dx dt. So I'm going to simplify. I'm dividing both sides of this equation here by 1.6 to get dx dt is 70. So that means that that speeding car is moving 70 miles per hour.